Now that we have distance explicitly as a function of the angle that we're shooting the object at, we can use a little bit of calculus to figure out the optimal angle, the angle that's going to optimize our distance. And since we only care about angles at from 0 degrees to really 90 degrees, let's constrain ourselves. So we're going to optimize things for angles between 0 degrees. So theta is going to be greater than or equal to 0 and less than or equal to 90. So let's see how we can do it. And just to get an idea of what we're even conceptually doing with the calculus, remember when you take a derivative, you are finding the slope of a line, an instantaneous slope of a line. And if you were to graph this, and I encourage you to graph it on your own, maybe with a graphing calculator, it'll look something like this over the interval. It will look like this, where that is the distance as a function of theta axis. And then this would be our theta axis. And we care about angles between 0 and 90 degrees. So if you were to graph this thing, so this is 0 degrees, this is maybe 90 degrees right here. The graph of this function will look like this. It'll look something like this. It will look something like that. And what we want to do is find the angle. There's some angle here. There's some angle here that gives us the optimal distance. So this is right here. This is the optimal distance. And what we want to do is find that out. And when you look at the graph, and you could do it on a graphing calculator if you like, what happens to the instantaneous slope at that optimal distance? What's flat? The slope there is 0. The slope there is 0. So what we need to do is take the derivative of this function and then just figure out at what angle is the derivative or the instantaneous slope of this function equal to 0. And then we're done. We will know this mystery angle, this optimal angle to shoot the object at. So let's take the derivative. So the derivative, we'll just use our derivative rules here. The derivative of, we'll call it d prime, I guess, or we could say the derivative of the distance with respect to theta is equal to, we're assuming that s and g are constants, so we don't have to worry about them right now. We could just put them out front since we're assuming they're constants. And then we could do the product rule to take the derivative of this part with respect to theta. And the product rule, in the product rule, we take the derivative of the first function times the second function. So the derivative of cosine of theta is negative sine of theta. Negative sine of theta. And we're going to multiply that times the second function. So that's times sine of theta. And to that, we're going to add the first function, which is cosine of theta, times the derivative of the second function. The derivative of sine theta is cosine of theta. I know it's a little bit confusing. All we did is we took the derivative of the first one times the second one, and then we took the derivative of the second one times the first one. Let me make it even more explicitly clear. We took the derivative of this guy here. So this is the derivative with respect to theta. And we took the derivative of this guy over here with respect to theta. We took the derivative of cosine there, multiply it by sine. Took the derivative of sine here, multiply it by cosine. Just the product rule. Now what does this give us? We can simplify this a good bit. So we could write the derivative d prime is equal to, we could keep this constant out there, 2s squared over g times. Now negative sine of theta times sine of theta, that's just negative sine squared of theta. And then cosine theta times cosine theta, that's just plus cosine squared of theta. Now, what we just said is we want to figure out the point, the angle at which this derivative, or the instantaneous slope, is 0. So let's set this thing equal to 0. So we just have to solve for theta now. Now, the first thing I do to solve for theta, is just divide both sides by 2s squared over g. If you divide the left-hand side by that, it cancels out with 2s squared over g. And if you divide 0 by that, assuming that this isn't 0, which it shouldn't be, then you'll still get 0. So this equation simplifies to, I'll write it in blue, negative sine squared of theta plus cosine squared of theta is equal to 0. Now, if we add sine squared of theta to both sides of this equation, let's add sine squared of theta to both sides, we are left with, these cancel out, cosine squared of theta is equal to sine squared of theta. Sine squared of theta. Now, both of these are going to be positive over the interval, so we're going to just take the positive square root of both of them, or the principal root of both sides of this equation. So let's do that. So you take the principal roots of both sides of this equation. You could do it that way. Actually, a more interesting way than doing it that way is to divide both sides of this equation by cosine squared of theta, assuming that it's not equal to 0 over this interval. So cosine squared of theta, cosine squared of theta. You could also do it using the positive square root, the principal root. Either one will work. But this is interesting because the left-hand side cancels out to 1. And the 1 will be equal to, what's sine squared over cosine squared of theta? Well, that's the same thing as sine of theta over cosine of theta over cosine of theta squared, right? You have a square divided by another square. That's the same thing as the numerator divided by the denominator. That whole thing squared. And what's sine of theta divided by cosine of theta? Well, that's just the tangent of theta. That's just the tangent of theta. So we have 1 is equal to the tangent squared of theta. Or we could take the positive square root of both sides of this equation. Tangent is positive over the interval from 0 to 90 degrees, so that's cool to do. So if you take the positive square root of both sides, you get the positive square root of 1 is 1. 1 is equal to tangent of theta. Tangent of theta. And then you take the inverse tan of both sides, or the arctan of both sides, and you get the arctan of 1. Arctan of 1 is equal to theta. And this is just a very fancy way of saying theta is the angle that if you were to take its tangent, you get 1. And you could use a calculator to solve that, or you might not. You might just know that by memory. This theta, the arctangent of 1, is 45 degrees. Is 45 degrees, or if you are dealing in radians, it is pi over 4 radians. Either one of those is going to work. So our optimal angle when we shoot this thing is going to be at 45 degrees. Now, what is that optimal distance going to be when we shoot it off at 45 degrees? Well, we can just go back to our original formula. We just go back to our original formula that we derived. If we're shooting it off at 45 degrees, what is the sine of 45 degrees? The sine of 45 degrees is equal to the square root of 2 over 2. You could use a calculator for that, or maybe you know it from the unit circle. The cosine of 45 degrees is also square root of 2 over 2. And if you'd actually just taken the principal roots at this stage of the equation, you'd have gotten that the cosine of theta has to equal the sine of theta over this interval, and that only happens at 45 degrees. But given this, we can put this back into the original expression right up here, our original function. So the optimal distance that we are going to travel. So distance as a function, the distance we travel at 45 degrees is going to be equal to 2s squared over g times cosine of theta, which is square root of 2 over 2. Cosine of 45 is square root of 2 over 2, times sine of theta, which is square root of 2 over 2. Well, what's the square root of 2 times the square root of 2? Well, that's just 2. Let me simplify this. So the square root of 2 times the square root of 2, that is 2. This 2 cancels out with that 2. And then this 2 cancels out with this 2. So then the optimal distance you travel at 45 degrees, all we're left with is the s squared over g. Assuming no air resistance, kind of an ideal circumstance. But no matter what planet you're on, how fast you do it, the best angle is always 45 degrees, assuming no air resistance. And if you do it on that best angle, you're going to travel s squared over g. So if s, going back to the original problem, if s is 10 meters per second, let's say s was 10 meters per second, and let's say we're dealing with a world where let's say gravity is equal to 10 meters per second squared, then according to what we've derived, your optimal distance, the optimal distance is going to be s squared. So it's going to be 100. It's going to be 100 divided by gravity. It's going to be 10. And if you square meters per second, you're going to get meters squared per second squared divided by the acceleration of gravity, meters per second squared. Second squares cancel out. You have a meter squared divided by meters. You're left with your optimal distance would be 10 meters. Pretty neat.